All right, so everyone's back from lunch. We're going to continue to go deep. The template master is here. Of course, you all know who this is, Andre Alexandrescu from Facebook. He's going to teach us how to write quick code quickly. Andre.
Hi, thank you. Don't applaud, I didn't do anything yet. All right, terrific. I told them to turn the lights a bit up so I can see you guys. I'll be taking questions during the talk, not after, because I think it's much more natural that way. I'm going to talk about the experience I've had within the past 6 months or so working on a project, which is one of the most interesting projects I've been on, and probably one of the projects that should go down in time as one of those famous skunkworks endeavors. The HHV and the hip-hop JIT compiler. Facebook has a large PHP code base, and we had a static compiler that would take the PHP code, parse it, rummage through it, and generate a huge C++ executable, a huge C++ source blob of source code, and then the C++ compiler would take that and compile in a couple of hours Facebook, the whole site. One day, one nut by the name of Keith Adams is like, you know what, I'm going to write a JIT for this because I think the compiler can be improved on as far as efficiency goes. And many months later, and with a couple of other folks, they had a working implementation of a just-in-time compiler for PHP written in C++, which was 8 times slower than the baseline, than the static compiler. So you gotta contemplate for a bit here what kind of grit it takes to have an 8 times slower implementation and say, we're gonna do better than the baseline. So many months later, with a much larger team, today I can't give exact numbers, but we are like well beyond 1.5 times faster than the baseline. And that has happened with like a dozen of awesome engineers, and then me. So I've been, for the past 6 months, I've joined the team. It was well beyond the time when all of this great stuff has happened. So to my name, I only have a few percent of these improvements. And to put this in perspective, you got to know that 1% in improving the JIT compiler translates in many years of salary for our best paid engineers per year in power costs alone. So if you shave 1%, you've made your salary for 10 years or so, right? And we're shaving like 1-2% a week. So this is kind of a very cool project to be on. Has a very clear measure of success, and I'm very happy to share here a bit of the experience I gained while working on this project with people who are really specialists in writing fast code. So lesson number 1, which actually originates from a discussion with Keith Adams himself, the initiator of this project, is that tweaking does matter. Because most people think, well, so you have the proof of concept, and then you tweak it, and you get like 20% more performance. Or you get like 2 times. So 2 times is good already. Like we double the speed when tweaking. Tweaking does matter, and there's a lot of projects that are things like even entire programming languages or compilers or implementations of complex systems that are a proof of concept, and it goes only at this much, and then nobody sits down and tweaks them to the extent that they actually make great products. So tweaking does matter. It's surprisingly how much. It's surprising how much, starting from something that's conceptually good, but in execution is wanting to make it like really compelling. I've discussed in December in a talk that's available online some sort of high-level tips for getting more performance out of the CPU. such as reduce strengths of operation, like use addition system multiplications and things like that. And minimize indirect writes through arrays and pointers, because those are very hard to register. And of course, measure everything and anything. That's an essential topic. Now, I don't want to repeat myself, so I'm going to talk about other stuff. But before that, I do want to insist that you must measure everything. So I copied a few slides from my old talk in here. So we all have intuition. And the intuition of programmers is as good as the intuition about the other gender, right? It's always wrong, right? Outdated and everything, right? So intuition ignores a lot of aspects of a complex reality. So today's machine architectures are so complicated, and there's so many variables in flight at any point in time that it's essentially impossible to consider them deterministic machines anymore. They're not deterministic anymore. So we make very often big mistakes when measuring, or when assuming things about what's going to make fast code. So for example, a good line of thumb is fewer instructions is faster code. And I've been browsing through, for example, like The Hacker's Delight. That's a great book, right? Hacker's Delight. And they have a number of examples. And some examples, they actually mention, if you measure this, it's going to do less instructions. But this instruction is so costly that actually the more naive code is going to be faster. So that's not always true. How about data is faster than computation? Right? That sounds like a reasonable thing to say. Like you don't compute, you have some cached, memoized, good stuff going on, right? Of course, there are many cases in which data is not going to be faster than computation because you have all these cache spills, and you have cold data, and you have array index issues, and you have aliasing and all that stuff, and it's driving the compiler crazy. How about the opposite? Computation must be faster than data then. Of course, that's also not always the case. So the only intuition you should be having, the one good thing that you should be keeping in your mind at all times is, I should measure this stuff, see what happens, right? So this is the one topic that's good, the one intuition that's good. And to quote a classic, who's actually still alive, Walter Bright, back there, measuring gives you a leg up on experts who are so good they don't need to measure. Okay. And Walter and I have been working on optimizing bits and pieces of project work on, and this has come like whenever we think we know what we're doing, we measure, and it's just the other way around. I do have a new piece of advice compared to my talk in December, which is prefer indicative proxy to noisy timings. Timings are good, but they're extremely noisy on contemporary machines. At this time, I'll be very honest, at this point in time at Facebook, we do not have a very reliable way of measuring things beyond like 1% difference. And I told you 1% is huge for us. So within 1%, it's noise. And that's unacceptable. Because of that, we use a number of proxies, a number of, features that indicate indirectly the execution time. Who can come up with a good proxy? What's a good approximation of speed? Loud. Throughput. Bytes per second, yes. Anything else? That's a good one, actually.
Use saturation under load.
Saturation under load. CPU, like how busy is the CPU? Excellent. You guys you have all of them. I have like 3 more and I'm done. Okay, there's temperature. I didn't think of that one, but it's actually very interesting. But temperature is like there's also external factors influencing it. Like yes.
Watt usage. What? Power usage.
Power usage. Yes. So power is a good proxy too. Latency. Throughput, latency, different things. Let me kind of talk in the small a bit. There's 2 good proxies that we can use, which are how many instructions were executed, retired. And that's a good proxy because essentially there are cases in which you reduce the number of instructions executed, but you don't reduce the time by a lot. But that can go on forever. So fewer instructions in the long term are going to mean shorter time. Another one is how many writes does your program do? And these are like very precise. That's a nice thing. Like number of instructions, number of like writes, how many writes do you have, how many reads do you have, and stuff like that. These are very easy to measure precisely, whereas time is kind of an evanescent notion in philosophy and in concrete, right? So we still use time as a primary indicator, but we also have these proxies for it, and we're looking whenever one of these indicators is off and the time looks good, there's a red flag there, right? So I'm going to talk next about data layout, which I believe nowadays is the number one issue in computer science and engineering as far as efficiency is concerned. Jumped a few slides here. So data layout is very important. And generally, the smaller you make it, the faster it is. And one interesting notion is that whenever you have an object, you got to look at the first few member variables, the first 64 bytes to be precise, because that's where the rubber hits the road. Apologies for the stereotype, right? But that's where things happen. The first cache line of every object. That's where that's where it gets red hot. You got to make sure that you don't put there things that are cold, that are set once and consulted like in the destructor, right? You got to make sure that you put there what's important to the object. And then later on, at the next cache lines, you can afford to put some colder things. Mind the gap. You got to know everything about how your data gets aligned. Plant static asserts in there. Make sure that your data looks exactly as you imagine it, and it has no holes in it due to alignment. And this is sort of a new thing, is avoid bit fields like the plague. Now, I'm actually going to get a bit into that because it's interesting. I hear someone, Herbie's laughing here. I'm sure it's with me, not right? Okay. So the best data, so our team spends weeks and months on designing data layout alone. Like for example, there's this notion in PHP called an array, which is one of the most idiotic, one of the most odd structures ever invented in computing science. So there's a PHP array, which is like at the same time a map, contiguous, a supposedly contiguous array, and a number of other things. A tuple, I don't know, maybe I'm forgetting a few. But it's an odd thing. And actually, our best engineer spends weeks and months thinking of how to make that array back in memory, how to put it in memory. So it's a big deal. So the best data types that I've seen are a few. You can't afford to spend that much engineering effort on many layouts. Beautifully packed, you don't waste any bits. It's amazing how much you can gain from one bit. You can put a lock in there, did you know? Like all this kind of stuff, right? They share layout over multiple types, which is kind of an unusual and sort of counterintuitive thing. You can have a data that changes type but keeps layout. And that's nice because you don't need to shuffle things around, you don't need to write much, it's very efficient. So you can change the data type from a contiguous array to a map or something, right? Without actually changing layout all that much, right? And this makes it real fast and interesting. And there's a harmony between storage and computation, which of course you measure only by actually sitting down and timing the code. If you get it too packed, then there's going to be a lot of work to kind of manipulate the data. If you get it too loose, you're going to have too much data, and the data cache is going to spill. So either the instruction cache or the data cache is going to give, and the key is to kind of put them in harmony somehow. And this is where the art is, right? So a simple lesson learned would be you want to sort your member variables by hotness in descending order. Like you go to hotornot.com, you see which is hot, and you put it first. Okay? That's how it works. Sort member variables by hotness descending. Put what's important in the first cache line. Okay. All right, so now let's get on to my favorite rant here, the bit fields. So you know what bit fields are, right? The colon for whatever, right? Raise your hand if you do. I want to see a forest of hands here. All right, those who didn't, essentially they're like, I'm not using that stuff. I'm not even acknowledging it. The problem with bit fields is multifolded. You can't get or set a bit field without a shift. And you cannot get set of the entire, I have like 4-bit fields spanning like 32 bits. And you can't kind of just put a 0 everywhere, right? And actually, there's a sort of a vicious circle here because bit fields were not invented for efficiency. They were invented for things like memory mapped I/O and device drivers and stuff like that, where you gotta put the bits there. They're not for efficiency. They're not for packing data. Yes.
I understand that you cannot set without a shift, but it seems that you can get without one.
You could get without a shift.
Yes, you just need to mask after.
You need to mask after. There's no intrinsic for that. That's what I'm saying. So there's no intrinsic operation for doing so. There's no primitive. That's what I mean. If the compiler were really like clairvoyant, if there were a lot of optimization effort on it, maybe the thing could improve. But the way I see it, there's a vicious circle around, which goes like, nobody uses bit fields for efficiency. Therefore, nobody in the compiler team spends time on improving them. And therefore, nobody continues to use them for efficient stuff. So it just goes on and on. GCC generates like awful code. If they wanted to generate like real bad code, they couldn't do better. And I hear there's a hand here from an LLVM guy who's going to say, if we do better, yes.
Have you tried LLVM?
I have not tried LLVM yet.
You should try LLVM.
I should try LLVM. And that's how the conversation went, ladies and gentlemen. All right. However, that being said, there's no primitives available for expressing bulk operations on bit fields. And let's see how we can improve on that. And sort of to wit, I'm going to confirm the stereotype that I never give a talk without a template in it. There it is. My coworker, Tudor Bosman, actually Google for him. He has a very nice blog, really cool. Bing for him, sorry. He devises a simple structure. It's like bit fields, and I'm going to define a few bit fields, 1 bit, 3 bits, 4 bits, and 8, for a total of 16 bits. And I'm going to be able to, store them in bulk, or I can get any one of the bit fields I want, or set it, right? Now let's see how to make this work. And actually, you have like there's a variadic in there, right? So and there's no. Okay, there you go. Does anyone see that red dot? Okay, catch it now, right? Okay, I can't see much of it, but I guess you can see it here. This is a variadic list here, so you can specify any number of fields, right? All right. So let's make this work. For that, I need some support code, which is kind of a bit uglier than it should. Under C++14, I could use const expert for that stuff. This just sums. Look at this static assert here down at the last line. Sum of 1, 2, 3, 6, which is sensational. This is what this template does, right? I don't even need to explain it that much. It's the classic recursion. I'm declaring a sum, and it's going to take one size, and the value is going to be the size, or multiple sizes, and the value is going to be the recursion. So I have a very simple template that sums a number of numbers. The second piece of support I need is a store type, which gives me, well, what's the store for storing 8 bits? It's going to be uint 8t, which is, all of these types are included in the header called.
Standard in.
Okay, so I heard two, neither of which was what I was thinking. I was thinking of cint types, but probably that's not it, right? But that includes the other, at least on the GCC. So, okay, talk to me. What header do you need for uint underscore whatever? CSTDINT. That's what I thought. Anywho, I'm making stuff up as I go. Is it visible? Is it like that obvious? Okay, so I declare store for any number of bits, but then I specialize it for specific bit sizes, and I leave it undefined for everything else. Meaning, whenever somebody tries to instantiate store with 7 bits or 15 bits or 9 bits, they're going to get a compile time error. There's no store for this particular size. So I have a store that defines me the support type for this number of bits. I guess with kind of this stuff and this stuff, doesn't write itself right now, right? I mean, this is obvious. So I say, well, template of any number of sizes, bit fields, and I say, well, store of sum of sizes value type is going to be my store. So that first line inside the definition is going to be my store, right? Wherever I put stuff. And then I have a really complicated friend declaration, which you're going to, it's actually motivated, but it's kind of weird. So let me skip it for now, and I'll get back to it. But essentially, bit fields has, I got, in 2 slides, I got as far as defining a bit fields that has a good store with exactly the number of bits I need, which is awesome, right? Depending on where you come from, it's awesome or like awful. So now we want a means to, for example, get one of these bit fields. So I'm going to get that position POS from a bit fields of as many sizes as I want. And I'm going to use this getImpl mystery function. The reason for which there is a get and a getImpl is that I need to place that 0 in there, which is sort of my iteration for the store. Like, give me the third field of a bit field. So I'm going to have to skip progressively the store so I get to my actual bit that I need. So get just forwards to getImpl with 0. And getImpl is where things get really interesting. All right, so stay with me. I have a template. It's unsigned position, unsigned before. How about them apples, huh? Before, right? So unsigned position before, and I have a size, the first size, and then more sizes so as to decompose things. And I say, well, it's going to return an unsigned and give me from this bit fields, give me the bits at position POS. So I need to do one masking and one shifting. Actually, I'm going to do it the other way. First, I'm going to shift, and then I'm going to mask. The way I'm going to do it is via recursion. So if I just so happen the position is 0, I'm there. So awesome. Let me skip that for a second. Let me explain the recursion first. So if position is 0 later, the last line is return the recursion. And the recursion is going to say, well, I'm going to bump down the position of the bit field, and I'm going to make progress in the bit fields list. Who can tell me why I put like all that position minus, it should be position minus 1. Like return getImpl position minus 1 and before plus size, because that's how I'm moving. I'm bumping the position down, I'm moving forward in the list. Who can tell me why I put those conditionals in there? Yes?
I think it's because that code needs to be able to compile even if it's never executed.
Awesome. All right. This is a great conference. I hate when I'm left there hanging, like, hey, can anyone, So yes, this is exactly why. I did not specialize this template twice. This is everything. This whole get from the bit fields at position POS is in one step. This is unusual. Most of the time, people, what they do, they put it in 2. They say, this is the recursion, this is the base case. All right? I put it everywhere in there. And that if POS equals 0 is going to be a runtime check, but in reality, it's going to be the compiler is going to eliminate it and everything. But my point here is that this guy still needs to compile, even though it's never going to be executed. The compiler is going to insist on that. To avoid sort of an explosion in infinite recursion, all that stuff, like, the integers like go overboard in 4 billion and whatnot, right? To avoid all that, I made it to recurse to itself if nothing happens. So I forced the template, if position is 0, then I'm going to recurse to myself. It's going to be an infinite recursion, and the compiler is going to be like, yep, okay, fine. And the optimizer is going to be, sure, I'll eliminate that code, and everybody's happy. Do I make any sense here? This is an absolute classic, right? From now on, I mean. Going forward in history. So this is like, people actually do this. It's sort of a common thing. The compiler insists on compiling. There's no static if in C++. So you put an if there, and then you kind of take care of it. All right. Oh, and by the way, did you see that size of ... Yeah, I'm asserting that I'm actually not accessing beyond the last position, right? This is the only use of size of ... that I know of that makes any shred of sense. Okay? And it's useful. I just used it. Awesome. All right. Does this all make sense so far? No. Okay. We'll go it over again because I still have like position equals 0 case. There's a question. No question. All right. So let me recap. Get me from a collection of bit fields with different sizes. Let me get back to the example here real quick. This is what I need. I have a bit fields. The first bit field has size 1, which is a Boolean really, right? And the second is going to have 3 bits, and the third is going to have 4 bits, and the last one is going to have 8 bits. All of these are going to sit in a 16-bit word, and I want to have an abstraction on top of all that good stuff. Because otherwise, we're not using this in production yet. Tudor has not finished the thing yet, but I do know we're using a lot of boilerplate that this would beautifully replace, right? So our goal is give me the bits at position 2, which would be 1, 3, 4, like 4 bits, shift them over and give them to me, mask them away. To do that, I have the store, I have all these good things, and this is where actually it happens. And what I need, if position is not 0, I need to bump the position up, like move him. It's an iteration really. So move the position up and take away the list of sizes, take the head off, which would be this first size. So this is the recursion part. Now let's get a bit to the position equals 0 part. Here, the classic case is this line here, the last return inside the if. Return bf.store, shifted down by before, and then masked away with what it should be, right? So this is what the bit field operation entails. This is what GCC would generate naively most of the time, right? But if the size is not 0, if it's 1, if the size is greater than 1, we have this. But if the size happens to be 1, I generate very different code. I'm going to mask first and then say different from 0. Why do you think I generate? Like it's a bit. Give me a bit at position 14 in this word. Do you really want to shift that bit down? It takes so many electrons, right? Do you want to really shift that guy down and mask it away and look at it? Let's just mask that guy in place and compare with 0. And if I'm masking it, it's 0, it's 0. If I'm masking it's not 0, it's 1, and we're done. And this is what that comparison does. That's much faster code, actually, my friends. And you know why? Because
It's just an and.
because I measured. There's a joke that I didn't get. What was it? Okay. Yes? Special instruction generated. Okay, here's the thing. You know that dictum that says you should only use -1, 0, and 1 as literals in your code, right? That's a nice principle to live into. Among these 3 kids of yours, -1, 0, and 1, you should have a favorite, which is, I'm using these fingers, so it's not good. So I have these 3, okay? Your favorite should be 0. 0 is special. Whenever you have anything that you can use numbers for, such as a categorical type, an enumeration, you're like, yeah, let me enum, like, it's a device, it's a screen, it's a keyboard, it's whatever. And you have an enum, a categorical enum. Put the most frequent at 0, because 0 is special. Now you know why the Roman Empire failed, right? They didn't know of 0. 0 is special. Why? Because a bunch of operations in the machine language of any CPU architecture is going to handle 0. It has special operations for 0. It knows what 0 is. It knows how to generate it. It knows how to compare against it. It's an implicit constant in a lot of operations. If it's anything but 0, then there's a second child that you should prefer, which is 1. There are just a few things in which 1 is special. Very few. And -1 is like, yeah, that's a loser, okay? -1, I don't care for that much. It's the black sheep of the family. Nobody invites them at parties and stuff like that. So prefer 0 to all other constants. Experiment. I changed to enum. So there's an enum which was, smart allocation, malloc, whatever, our own allocator, malloc. And I swapped them around. There's a 2% loss in efficiency. Why? Because everybody compared against the first one. And as soon as I swapped them, there's a comparison against 1. And now the instructions were all different. So 0 is really good. But that's a mini lesson because I consider that a micro optimization. Nevertheless, I do think it's worth mentioning because it can have such a big impact after all. And then once you have this, you can get better primitives than the built-in bit fields. You can have things like, I want to set the bit fields, of course. But I can say, get me the bit field, but don't shift it away because, I may have what it takes to, I don't need the shift part. I just need the masking part. So get no shift, set no shift. Mask@, give me the mask, a constant, the compile time constant that's going to mask me a bit field at a given position, and give me the whole store and set a whole store. And these I can use gainfully for packing data in as few words as possible. Much better than bit fields. Now I'm going to talk about a really cool word, so I thought it's worth it. Devirtualization. I'm not even sure I'm pronouncing it correctly, but it's a cool word, and you should remember it. Who knows how virtual functions are implemented in the typical C++ implementation? Raise your hand. vtable, vptr, all that jazz, right? So we have a vptr which, 64-bit models is going to be 8 bytes at the beginning of layout per base class. So you can have multiple vptr in the same object, right? This is just going to be a layout thing. So all of a sudden, I'm expending 25% of that mythical first cache line in my object. I'm spending it on the vptr, right? So that should already kind of, be like, if I'm concerned about efficiency, that doesn't bode well, right? It bothers me a little, and it's an expenditure that's implicit and unavoidable. And the cost of accessing a function is going to be 1 to 2 loads, depending on what your pointer to object is. But usually, you start with a pointer to the object, and you fetch the vptr, and you go to the memory address by the vptr and do the index tasks with a constant index. Then you get a pointer to function, and you call the function. That sounds like a lot, right? We'd like to improve on that. Of course, it's very fast because it's like billions of gigabytes of whatever, right? But there's still a lot of work. And one hidden cost that few people remember, although it's kind of understood, is there's multiple assignments to the vptr during construction and destruction. Remember? Why is that? Someone else. Yes. Loud, really loud.
Because it changes type as the constructor runs.
Right. Right, it's exactly. So first it grows into eukaryote. I'm making up words. First the cell divides and becomes a eukaryote. Then it becomes an embryo. Then it becomes a dinosaur. I don't know. Then it becomes a maggot. I got the wrong order. But you see what I'm saying? So the object grows. It repeats the phylogeny, if you wish, right? So the object kind of transforms itself as it grows and becomes a better and more knowledgeable object. And the vptr reflects that during construction. During destruction, that's the whole thing. The film turns backwards and all that jazz. So interestingly, these assignments to the vptr are very hard to elide by the compiler. They're hard to detect as dead assignments because usually there's function calls in between and all that stuff. So that's a cost that's pretty steep actually for heavily used data structures. So keep that in mind. So virtual dispatch does have a lot of merit. It's been a fixture in C++ since forever. It promotes flexibility, decoupling. I don't even need to mention all that stuff because it's really old. One sort of new thing that I would like to mention is that automatic load balancing of I cache, instruction cache. What do I mean by that? So if you use a hierarchy with different types of objects, and use virtual functions for dispatching, there's going to be some nice load balancing of the instruction cache. Why is that? All right. I know you know. So there's one gentleman here who knows like everything, but I need someone on this side here, for example. This side is like, what's wrong with you guys? People on the left, yes?
Because all the vtables are in the iPad?
Because all the vtables are in the iCache. That's kind of getting there, but what I meant to say was, if you have a type that's very intensely used, it's used all the time, it has its own primitives, and they have a type that's very rarely used, they're part of the same hierarchy. The nice thing is with virtual function dispatch, you're seldom going to load the instructions, the code for the unused guy. You're always going to load the instructions for the used guy. Those are hot. And these are cold, and the vtable dispatch is going to ensure that only the hot stuff is going to be actually loaded. Yes?
At the same time, there's been a lot of evidence, especially for people doing things like video games and stuff, that if you have a collection you have to iterate across all, calling virtual functions, you can end up pushing stuff you're going to need in a minute out of the iCache because you keep calling down into different classes. And they typically advocate actually sorting contents by type in order to avoid that problem.
Awesome. Scott said in very many words the following. Okay, well, I'll say it in even more words and with a lousy accent and all that. Let me try. So essentially, Scott's point was, well, if you have an iteration across a vector of pointers, I presume, right, and sort of call the method for each, if the hierarchy is diverse enough, you're going to end up thrashing the iCache because you're going to load some instructions that you need, and then you're going to throw them away because you're loading some other instructions and so on. And therefore, gamers, what they want to do is sort a priori the vector by type. And that way you kind of load this guy in iCache, and then load this other guy in the iCache in the hierarchy, and then you load this other guy in the hierarchy in iCache. And that's great. Okay. Thank you. So you see what I'm saying here, right? There's some sort of an automated load balancing of iCache, of course, which is exposed to its own thrashing and stuff. The disadvantages, finally we'll get there. Wasted space in the hot zone, as I said. The hot zone, the first iCache, the first cache line there in the object, 1/4 of it is going to be wasted on the VPTR. It's relatively costly. I would like to reduce on that. On those dereference costs. Performs poorly on small and closed hierarchies. It's going to be open-ended. Think of this. You're paying for potential flexibility of the virtuals, not for the realized flexibility. So as soon as you put a virtual in there, you're like, well, I'm opening myself for flexibility down the road, right? But even if that function is not overridden, the compiler, without global information available, is going to have a very hard time proving that you're not using that flexibility, and therefore is going to be forced to do indirect calls when they are not warranted. There are interprocedural analysis called class hierarchy analysis, which actually takes a whole application and looks at what functions can actually be devirtualized. But this is a sort of a tall order for C++. So we're paying for potential flexibility, not for the flexibility we're actually reaping with virtuals. Of course, there's always switch. And, well, switch has its own issues. And if you sit down and measure, it's going to kind of work for up to like 7 branches. Depends on a lot, actually. So we're talking about a handful of branches. Small hierarchies. Mixes code with hot, which is a sin, actually, for efficiency. And you have like code, it's an anti-modularization device. Like really switch on type is not something that we want to do. So what people do is they do vtables by hand. So I have a class, and it has an actual vtable in there with 2 pointers to functions. One is get, one is set. It could be as many as you want, right? So that's my vtable. And then I have, this is a trick, I have a little tag here which is just a small integer. And then I have a static vtable which is going to be indexed by the class, right? So to call get, I'm going to take the vtable, I'm going to index it into tag, I'm going to fetch the member called get, and I'm going to call it. And to set, I'm going to do pretty much the same thing. Discuss. Destroy. I don't know, ruin me. Yes.
How can this be better than just, I'm not seeing the advantage. Obviously, if you're not going to be calling virtual functions, then you don't need virtual function mechanism. But if you're going to be calling virtual functions, then you have to have one indirection at least. Right? You can't avoid the indirection.
Okay, so how could this be better? So there's one good thing, which is this small integer here. So instead of using a pointer in the hot zone, I'm going to just use a few bits, right, for encoding the type. So there's a gain. But actually, this is less efficient than the classic virtual approach. And here's why. We're looking at, whenever I want to call a pseudo-virtual function, I'm going to fetch VTBL, which is a sort of a compile time constant. I'm going to index it with a variable. And the variable is going to be multiplied by what? Size of vtable. I mean, it's an array of, you see what I'm saying? You're going to index this tag. You're going to pay for multiplication as well. And then you're going to do a multiplication, you're going to do an indexing by a constant, which is get to the field called get. And that's going to get you to a virtual function. That's actually more costly than before. It's worse. So how do we solve that? All right, so here's a trick I learned from Ed Smith, my coworker, which goes as follows. You arrange the vtable vertically. You don't put it like, I have a table for class A, I have a table for class B. No. I have a vtable for class A, I have a vtable for class B. I have functions, the get function for different types. I have the set function for different types. And let's see what this gains me. Okay, once you're going to get this, it's going to be like, what? What is going on here? Okay, so let me put some type defs in place because I'm going to do a lot of casting and stuff. Like, let's say type def void is a function pointer. So far, so good. Then I'm going to have, this is my get and set types and whatnot. No problem. Here's the interesting part. Static, function pointer, VTBL, total classes, total methods. And as I'm sure you know, in C++, you read declaration from right to left, right? Your right, not mine, right? From your right to your left, right? Oh my God. Okay? So essentially, this is actually I'm putting things in a way backwards. Because when I want to index them, I'm going to say, let me fetch the vtable pointer, which is a compile time constant. Nice. So far, so good. I'm going to index it by a constant first, which is like the first function is 0, the second function is 1, and so on. So I'm going to index it by a constant first, and then by a variable. And the variable is going to be multiplied by what? Size of function pointer, which is a constant, which is 8, which is, you know what? The machine loves that. It's part of the addressing mode. Multiplying by 4 or 8 is implicit, is part of the addressing mode. It's one operation. It's zero cost. And then I'm going to get the whole thing, and I'm going to call the function. So here's what happens. Adding a constant to a constant address, multiplying that variable with 8 by 8, and adding the result to address, all of this is one addressing mode on Intel. Is one instruction. Get me this guy. Okay? 4% faster. Bottom line. I'm talking bottom line. For one type, you replace this, you do this for one type, you get like the win. Of course, there's ugliness to it because there's extra casts. I need to cast this guy, from a generic FP to FP get and FP set and all that stuff. So it's not all that convenient, but it is much faster. Yes?
Couldn't you eliminate all the casts by instead of having a 2D array, having n 1D arrays, each of which is properly?
Yes, you could have n1D arrays. And, if the wind blows the right way, then they're going to be adjacent in memory, so it's good. And I think it's a good idea. Yeah, I think it's worth measuring. I'm not committing to anything. Herb, destroy.
Just
meta question.
A meta question.
Normally when people talk about number of instruction count, including vector instructions, it's usually dominated, you have to first make sure you're not dominated by memory access. Is that the case here? I haven't grokked the memory layout here.
Dominated by memory access, reads.
Like if you have to wait for L2 cache, it doesn't matter how many instructions you say.
Oh yeah. Actually, no. Actually, most of the time you want to have a tight cache. So whenever you spill the cache, it's very visible. It's like, whoa, that went really bad. And actually, that's very cache friendly because you have a very compact table holding all the virtual functions. And then when you initialize this table, I'm seeing Herb nodding, which I presume is a good sign. So once you load this, you can do weird things like you don't have a hierarchy anymore. You have a sort of a federation of types and functions. And you can assign functions from different types to different types. And this whole layout thing, remember, use the same layout for different objects. This comes into play. And it's all like sort of a wonderful bucolic party there, right? It's awesome. All right. So lesson learned, which I had no idea about this until like 3 months ago. And they told me like, oh, this is actually this whole pile of stuff is one instruction. I was like, oh, what's going on here? This is amazing. So this is why it's so fast. So do know about your architecture's primitives. Our engineers who do know about how Intel works or how ARM works or how whatever architecture works, they're going to write much better code for efficiency than those who work in the abstract. Finally, I'm going to talk about a pet peeve of mine. I have 13 minutes here, and you know what? I have the microphone already, so I can take advantage of it. To elide or to move? That is the question. You know what I'm talking about. C++98, oh, avoid passing by value. Don't return by value. Don't do this. And then C++11 comes up, and oh, we have now move constructors and move assignments and trefref and all of that good stuff. And just use values, more everything. No problem. And I see Herb shushing me already. I fear that this is going to be one of those cool things, new to C++ relatively, that are becoming a dogma in some people's minds. Some people are going to just take it uncritically. They're going to say, oh, move constructors are going to just take care of it, so values everywhere. And that's not the case. And I'm going to make a few arguments about that. So the efficiency argument is very simple. Move construction is some work. Notably, whenever you move from an object, you got to write to that object. You got to write the null state to it and whatnot, right? And actually, those writes are very hard to elide by the optimizer, because it's very difficult to prove by the optimizer that those moves are dead and they're not going to be used anymore. And elision, which is available since C++98, is zero work, right? So this fantastic insight came up to me, and probably I'm going to patent it someday, which is, where was I? How about that? No work is less work than some work. Which is pretty an awesome thing to live by, right? So let me get back to more explanations here. Now we have the composability argument, which is just as interesting. Consider this: appending to a container a string is cheap because you just append, it's constant time pushback, whatever, in the long run and whatnot. So appending to a string, for example, is cheap, but creating one and concatenating them, building more containers from smaller ones, is difficult because you gotta, allocate the memory and free the old memory and all that stuff. So returning a container by value is worse than appending. Case in point, we had some parsing routines at Facebook since time immemorial. So there are parse routines and formatting routines, and they return strings by value, for example. And then you want to build a longer string out of a lot of other smaller strings. And you have this problem with a lot of temporary strings springing out of thin air, and you can't, essentially it's an API that you can't use efficiently. So we had to change that to an API that actually takes the string by reference and appends to it, and all was good. So that's the composability argument. Returning containers by value is actually less composable than appending to an existing container. And then I have the, what do they say, the last argument of kings, right, on the cannons. You know that one? Okay, Louis XIV, the king of France, he had this on his cannons. He had this inscribed, the last argument of kings. Like my last argument is going to be a cannonball right at you, okay? Which is, the measurements argument. This is the ultimate argument that you can make as a programmer. And let's actually take a look at two APIs. API number one, give me the next line. It's going to return the next line, including a terminator or the empty string if the file is done. I have a second API, which is slightly less elegant by some people's taste buds. Whoa. Okay, that was badly timed, like I'm lying here. API 2 is, give me the next line, put in the string, and return a Boolean, which is false when you're done. Now, here's the thing. Of course, there's sort of an internal jokes here because I'm talking about efficiency and I'm using iStream. If you really want to ruin your reputation, credibility, and career, you just use efficiency and iStreams in the same sentence. Pretty much done. But let me take that risk. And actually sat and measured this whole thing. Like, what if you use both APIs and they do the same instructions, they use getLine and whatnot and all that good stuff. Which one do you think is faster? The same? You're going to be disappointed, my friends. The version by reference was 2.7 times faster for short lines and 1.6 times faster for longer lines, understandably so. How slow is going to be yours? Pick your line length. Why? Why are you looking at such a big overhead? It's I/O. The part of reading bits from file is supposed to be the slow thing, and the little detail of allocating memory and making room for it is like a detail. Why is this API so much worse than the second? Yes, Stefan.
Were these measurements conducted on an implementation that has the small string optimization? Because if you didn't, then number one would allocate even like 8 bytes, and number two would just reuse the existing storage. With the small string optimization, I would not expect that.
Right. So maybe surprisingly, my implementation, from what I see from the numbers, it does not have the small string optimization. So, but that's a good remark. But the general question remains, why is it so much slower? Yes? Did you try LLVM?
No. Wait for it. To clarify, GCC hasn't switched their default string to use small string optimization because it's an ABI break. So if you're using GCC's standard library, you don't have small string optimization yet.
All right.
It's behavior. The other interesting thing is, have you tried LLVM?
Yes.
Is it possibly because of the atomic reference counting inside of string so that the move constructor is not as cheap as it ought to be?
Oh, guys, this is not the answer. No, it's very far from the answer. Yes, in a second.
STL mentioned reusing the buffer in the string, which is, depending on what code you wrote to test this, the reference version will reuse the buffering and return by value.
Okay, this is it's cold. Yes.
Sorry if I missed it, but this sort of relates to several questions. Which compiler and especially which standard library implementation did you use?
It was GCC 4.6.
Okay, copy on it right.
Yeah.
So
Yeah, no, I also use swap just to make sure I'm not depending on any vagaries. So I use swap, which is guaranteed to be the most efficient. Just like move, I got the same results. So it's thoroughly checked. Yes.
My guess would be that because the second API uses the same memory space and it's just
Gosh, thank you so much. Come on, folks. This was it. Oh, that's what he said?
Yeah.
Okay, sorry. No, but some of the answers were wrong. So this is very simple, really. Every call to next line, a new string will be allocated and returned. At the end, the string is going to be deallocated, and then a new string is going to be allocated and then deallocated. Every pass through the loop, a new string will be created by design, by the design of the API. The second API is going to, at the end of the whole, reading a whole file, what's the capacity of the string? The longest line in the file, which may be a problem on its own. If you have a file that has the fifth line has 5 billion characters. And then it's like, 5 characters. So that could be a problem too in some arcane cases, but it's at least you can solve it without changing the API. So this is one problem which is pure API overhead declared by the design, and it's not an implementation matter. So do not think that actually deref and move constructors are the automatic solution to all problems. And you can just return by value without actually thinking about it. Yes?
Slightly more than just API design, though, because the second one, for example, you've got to know to put the string outside the loop. So you put string S inside the loop, you call that function, and you
Right. So I think the point was the typical use for this is going to be inside of a loop, so you got to think about it that way, right? So if you have an occasional need for a next line in a file, yes, the APIs will be just the same. All right. Yes? Really loud. You got to be really, really loud.
Okay, going back to one of your earlier points, when you're reusing the buffer will be hot.
The buffer is going to be hot in the cache as well. Yes, so it's going to be reused over and over again. So it's kind of the perfect design there. Very nice. So in our project, it's a multi-million lines of code project. So you got to make sure that you have some simple rules that are easy to remember and use for how to elide things. We have a very simple approach. There's two cases, URVO and RVO. Unnamed, named, return value optimization. And again, there's a few cases that are, compiler dependent and kind of smart and stuff, but we're going with something that almost always is going to deliver. URVO is all paths in a function return our values. It's all expressions with our values. Right? std move qualifies, by the way. std move qualifies. Yes, what? Okay, slap face from Scott. This doesn't.
The problem is that L values can also be treated as R values in that case.
Give me a second, because we have NRVO. No. You can't. No, that's not going to be a lesion.
All right.
That if you put an L value in there, it's not going to be elided. Scott nodded. Let it be in the record that Scott nodded affirmatively. So two simple cases, all paths. Huh?
With many nods.
With many nods. He gave like at least 7 nods of 2 inches or more. Yes, Stefan.
I believe for the unnamed return value optimization, you must have all paths returning PR values. I believe that X values do not qualify because they're not actually being constructed there. So
Like std moves return.
stood move is an X value, so that
Right.
does not qualify. And I will be talking about this in my next talk.
Well, let me put it this way. As a man, you got to take risks. and bow graciously whenever they don't pan out. So std move does not qualify, and you're going to hear all about it in the next talk. And the name return value optimization is also very simple. All paths return the same local variable, the same. It's got to be the same. You can't mix the two. It's going to be pessimized. So you declare a string or whatever you want to return at the beginning of the function or wherever, and everywhere in the function you're going to return it, and you're good. It's going to be elided. The copy is going to be elided. For everything else, you can assume an extra copy. And actually for GCC, that's almost rigorously the case. And that was funny. With this, I'm done. Let me actually summarize what I talked about. Tweaking does matter. You want to mind the hotness of your variables, group hot variables together. Know about your architecture's primitives. Understand the implicit cost of operations, such as virtual calls, such as construction and destruction of objects, which is a bit more involved than actually the source code may indicate. And no work is less than some work. And with this, we have time. We have 40 seconds, so hurry. Questions? Yes, Charles. I did try LLVM.
So I have one comment. Just so you know, I think Richard Smith is going to try and get move elision into the standard so that we can align moves as well as copies, which will fix a category of the problems that you
Give Richard Smith a hand. Thank you. This is awesome. No, this is actually bigger than one may think.
The other thing I wanted to ask about is you talked a lot about at the end an interface which baked in a customization to the interface design itself, and I wondered what your thoughts were about where the trade-off point is between making an interface easy to use versus efficient, especially in light of certain compilers, which I won't name any particular ones, which work very hard to decompose these abstractions in a way that still allows them to be optimized. I mean, I think the interesting thing is that if you go back to your bool versus string return thing, so you went way too far. No. Yeah. So there's nothing inherent about this that says you have to generate the slow code. Right? And I actually think that it is possible within the constraints of the language to optimize this. It's mostly that our implementations aren't quite there yet.
Okay.
But I'm curious, where you think that trade-off lies.
This is interesting on more than one level. So let me put it this way. If you use the source, if you actually look at the source code, I don't have it on the slides, but if you look at the source code for the two, actually the second one is slightly better because it's a while, not, the other is like while and you're gonna sign inside the loop or you put it inside the loop and it just looks kind of backwards a bit, the first API. The second API is like while next line, do this, or for whatever, and define the string at the beginning of the for, and it looks beautiful. So, the short answer would be beauty is in the eyes of the beholder. And I'm really curious about how this could be made much more efficient. I can think of like inlining and post-inlining optimizations and all that good stuff, which LLVM is actually very good at. At some point you gotta draw the line. What I can tell is for our team, the HHVM team, the code is not beautiful. How should I put it? Everybody understands why we need to pay certain prices for efficiency. So it's understood. It's a team of brilliant folks, and then me. So it's a team of very good people. And there's a mutual understanding that there is some price to pay for 5% of efficiency or even 2 or 1% of efficiency. And that price is going to sometimes be more bloating, uglier code, more coupling, less modularity. So it all depends on what your priorities are. Stefan and then Herb, and probably we're done. Yes.
Well,
Stefan?
actually, online after those two, okay?
Okay. Yes, destroy.
I actually cannot believe that I'm defending IO streams for both elegance and efficiency here. I seriously cannot believe it. But stood getLine non-member actually takes your second form. For
Yes.
string s, getLine c
Right.
and s, and that's actually the easiest way to write the loop from the user's perspective.
Yes.
Ignoring the library.
But then I encapsulated getLine in these two APIs, and essentially I do the same operations except that I
Well, I mean,
put them in different
getLine
APIs.
literally has
Yes.
the second form except it returns the iStream
Yes.
ref. So
Yes.
does that.
All right, Herb, and then 2 online questions?
Yep.
Okay, go ahead, Herb, shoot. Loud.
Similarly,
Can we get a little mic, please?
Mike for Herb? Thanks.
Similar, I guess IOStreams does this in other places because I always thought of while C and shift S. So Bjarne designed that too, if I've got my memory right. Second, I don't know if you've talked about this, but another reason why optimizing move is really important and move has to be cheap and we can't just rely on, move easy, don't worry about it. You might have mentioned this, but Howard Hinton taught me this. Is because all of the vector is now move aware, all the algorithms are now move aware, which means move actually dominates. So that actually making your move percentage-wise faster actually has a material effect on your entire algorithm now because it's that much faster. So I thought that was an interesting point. I didn't realize that.
All right, just to make sure everything you said agrees with what I said. Yes. All right, online questions.
So Matt PD has been asking a few online. So Matt, we're getting to you. Andre, your talk really reminded me of data-oriented design. popular in the game dev community. The practice of designing software by developing transforms for well-formed data where well-formed is guided by the target hardware and the transforms that will operate on it. What are your thoughts about that?
My expertise is insufficient. I can barely understand most of the phrases you said.
Okay, so the second question is, Andre, member order also affects initialization order, which becomes more and more important with concurrency synchronization features like queues and, if necessary, simpler synchronization structures. What if you can't move hot data first because of correctness issues due to initialization order? That's a really weird sentence.
No,
But do you
makes
understand?
sense. Yeah.
Okay.
So first off, like there's sort of a disclaimer here. Like I talked in the past about concurrency. This was not concurrency. It was straight line because we're already distributed up to wazoo at Facebook, essentially. And this talk is about how to make one of these many threads, 10,000 threads or whatever, on one machine on many thousands of, tens of thousands of machines out there. So essentially, we are already expanded horizontally, so if you wish. So I'm talking about the vertical here, which is you load a page in PHP, and the thing is you want to get the page loaded as fast as possible. And this is that this talk was about. And essentially, it has no threading aspect. It's just essentially within one thread of execution, serial performance. With that disclaimer, let me put it this way. What would you choose between correct code and fast code? Right? Fast code. Good answer. So essentially, when correctness is at stake, you got to do what you got to do. So, you know, but again, good design, I notice, is always, there's never something in life, if you wish, that's only positives. Whenever I have a slide with pluses, I make sure I throw in some minuses because I know there are there. There's very few engineering topics, items, or decisions or designs that are mostly pluses. So you got to do what you got to do. Good design is a balance of trade-offs. Is there any other online?
Well, one person would like to know what on earth you guys are doing in your team that, you know, essentially you needed to do this devirtualization stuff.
This was specifically created by Ed Smith for HPHP array, which is the implementation of the PHP array, which, as I said, is a data structure that is so bizarre it defies any reason whatsoever. And you know, when you encounter something that defies any reason, devirtualization sounds like a right word to address it.
And then another question would be, I guess Chandler sort of touched on this, but Saul wants to know why can't compilers just deal with this devirtualization madness?
Why can't compilers do it?
That's his question. Why not get the compiler to always do this for the devirtualization, which it seems you were doing at Facebook, but compilers do this in general. That's his words.
I would say, I think many people in this room can actually give a better answer, but the way I see it, compilers are designed for flexibility and sort of the common case and pleasing everybody. And the virtual mechanism as designed for the typical implementation of the VPTR vtable duo are designed for maximum flexibility, making everybody happy. It's a good enough design. It's reasonably efficient. It's pretty good. It's actually more efficient than most other languages I know, right? So thank you. So it's a good mechanism. The point here is that we wanted some extra oomph because that extra oomph is, you know, is a really special niche case, and we need like the hottest thing that the silicon can offer. Question, there's one more.
Two more questions.
Two more.
Over there.
Okay, you should know we're minus 8 minutes. You're eating into your break, guys.
We're good, actually.
Awesome.
Okay. Just a follow-up to the comment online.
All right. This is the last question.
I think it's possible for the committee to standardize something like to enable the devirtualization, because it reminds me the final class in Java. If you mark some branches of your inheritance hierarchy, then actually the abstraction is limited. It's a closed abstraction. Right. If we have something similar in standard that we can have a fixed graph in a module, we can actually optimize it.
I think, correct me if I'm wrong, leave you the microphone for a second. If I'm not wrong, you're referring to things like sealing hierarchies, sealed?
Yes.
Okay, you can give the microphone away. So, so sealing would mean I have a virtual function, I'm overriding it here, but it stops here, and I'm never going to allow it to be overridden again. I think that's a good idea, and I do think that there's a lot of efficiency wasted in your typical programs in C++ by functions that are virtual that really shouldn't be, or in a particular application they needn't be, even though in the library they should. So there is value in that, and I think sealing would be an interesting thing to explore. People in the community, let me know if the sealing is being explored at all.
So, yeah, final does sealing.
Final does it. Give them a hand. All right, come on. Awesome. Yeah, this is, I mean, it's like, I don't even need to be here. They could.
So
Yes.
I wanted to clarify, as an answer to that question, there's a good 10, 15 years of optimization research around devirtualization. GCC and LVM and lots of other compilers do it. IBM's compiler is actually, I think, the best in the world at it. I think they actually wrote the book more literally than most on how to devirtualize. The other thing to keep in mind, though, is that a lot of these do require whole program analysis. IBM's compiler, I believe, you can correct me if I'm wrong, in whole program analysis can essentially do just tremendous feats of devirtualization. And sealing classes, sealing methods absolutely helps with that. I do know that both LVM and GCC do not currently take advantage of final to the full extent. But it's new. We're working on it. We'll get there eventually. I think that there's actually a lot of interest in devirtualization in the optimization community. From an implementation stance.
I had no idea, so I'm very glad I inserted in this talk. With this, folks, we're done. Thank you so much. Thank you. Thanks. Beautiful.